So what it looks like is this part one, will actually be broken up into 3 lecture segments. So let's see what we got. A lot of this stuff, it's quite possible you learned it in high school or even grade school. It's some wonderful things about our planet. One of the things that we see with regard to our planet is that actually its rocks recycle. So the material that's in the inside of our planet actually kind of ends up as rocks on the surface of our planet, and then those things on the surface of our planet, rocks, will be brought back down. This we'll talk more about later too. It reminds me of like Frankenstein kind of stitched together. If you're familiar with this idea of plate tectonics, the fact that the Earth's crust, we'll talk about kind of the layers of the Earth, floats around, that's kind of what's being shown here. Oops, sorry. So the material cycles between the surface and the inside of the Earth, that material being rocks. I almost feel like we're back in astronomy. So we talked about the fact that the age of our Earth is we mark the birth of our Earth at the same time as the birth of our sun, and that was about 4.6 billion years ago. So at that time, then it had all of the material that was going to be part of the planet Earth. Well, most of the material. I don't know, I think in astronomy I talked about our Earth keeps picking up weight all the time because of meteoric material kind of falling through the Earth's atmosphere. But anyway, we're going to talk about different types of rocks, and one of the important types of rock is what we call igneous rock. And there's 3 types of rock. And this igneous rock is the rock that was basically present as the initial Earth's surface cooled. Or we talked about recycling. Basically, it's just rock that kind of cools in place. That's igneous rock. Now, early on, our Earth had some internal heat, and our Earth still has internal heat. Now, it's not the same type of heat as the sun has, because, of course, the sun has heat because of nuclear fusion, but the Earth has heat because of in chemistry, nuclear chemistry, just simply nuclear decay, where one element is decaying into a lighter element and releasing subatomic particles, gamma rays, or some little bit of, and also energy. That's my point. So when it says radioactive decay, that's what's actually we still have some of that thermal energy going on, being released in the core of our Earth. But anyway, there's even more radioactive decay for the earlier Earth, and it created kind of these molten conditions, or creates these molten conditions, this liquid rock that we see, and we have some kind of these little pockets, little pus pockets in the interior of the Earth. Planetary differentiation, or differentiation, is actually, I likened it to like maybe Italian dressing. I might have talked about this when we talked about the formation of the planets, where heavy things sank just like Italian salad dressing, and light things rise just like Italian salad dressing. So when we talk about the structure of the Earth, what we're going to see is that the core of the Earth actually has these materials that are very dense, and the surface of the Earth's crust, has these things that are very light. So speaking of the core is going to be the center of our Earth, and it's mostly the element iron. In the core of the Earth, it's actually very hot and very dense. How hot is it? Oh, about 6,000 Kelvin, 6,000 degrees Celsius, which is a little bit hotter than 6,000 Kelvin. So 6,000 degrees Celsius, not hot enough to obviously begin nuclear fusion, and it's a fair bit of pressure, 3.5 million atmospheres. Let's call that a fair bit. Oh, sorry. And these are the conditions at the Earth's center, the Earth's core. We're going to see actually the core actually has 2 parts to it, an inner core and an outer core. So I will end up breaking up these 3 layers of the Earth a little bit, but in general we can talk about 3 zones of the Earth, from the outermost going to the inner. So crust, obviously the outside of the Earth, like the crust of your bread, crust of the Earth. And then we have the mantle. We'll kind of talk about, it's a little more complicated than just the mantle, but than just one layer. And then we have the core. Very good. A little bit about those three structures of the Earth's interior, or I guess the crust is the Earth's interior, but the crust covers the whole Earth. Now there's oceanic crust and then there is continental crust. The oceanic crust is a little thinner and denser, and the continental crust would be the crust that's associated with the non-water surfaces of Earth. It floats. It's a little less dense. Okay, so with regard to ages of these two crusts, we can see that, where's my pen here? The oceanic crust is actually younger, and it's thinner, and it's less dense. The continental crust is older, and it actually is thicker, and it's less dense. And those have consequences, or there's some reasoning behind why that is. The Moho or Mohorovičić discontinuity. Now, if something is discontinuous, that means it stops. So actually, this discontinuity is just talking about the place where two important layers of the Earth's Earth meet. So this discontinuity place is between the Earth's crust and the mantle of the Earth. And we're going to talk a little more about this, but how do we know what we know about the interior of the Earth? And there's many different ways, and one of them is to actually count on waves, like energy waves, concussion waves, traveling different speeds or differently, being reflected or refracted differently in different types of material inside of our Earth. So what's up with the mantle? Well, the mantle's below the crust, and actually the mantle's pretty darn thick. You're looking at 80% of Earth's volume is the mantle. It counts for 2/3 of the Earth's mass. So remember, as we go closer to the Earth's core, the matter there becomes more and more dense. How do we know the overall structure of the Earth? Like I said, seismological data. That goes to sending a wave, like a shock wave, a percussive wave through the Earth. Now, how do these percussive waves come? Well, they come in the form of earthquakes. They also come, I've read recently, in the form of detonations, nuclear detonations. But we see how that signal goes through the Earth. Also, we can study space rocks and get a sense for what our Earth must be composed of. The other thing makes sense is we can understand the interior of our Earth by what our Earth shoots out, and that would be volcanoes. What material our volcanoes shoot out. So then we get to the third part of the Earth, and that's the core. The core makes up about 15% by volume and 1/3 of the Earth's mass. And I think I might have mentioned the core actually has a solid part in the middle and an outer part, a liquid part outside the core. I watched this video recently, and it might be one that I end up having you guys watch, in that the core, the solid part of the core, actually rotates in a different direction as the liquid core kind of goes slower. And it's that rotation. Remember, the core is mostly made of iron, and iron is great for being charged. So the core actually then is moving charges that creates the Earth's magnetic field. So one of the things that strikes me is if we're trying to look for, these are waves. So say we have an earthquake that happens up here. Well, you need to have a scientist here, or at least measuring devices here, to understand how that energy wave goes through the Earth. Is that not cool or what? Oh, here's one for you. So here's where the earthquake happens, and then what about having to have a place over here, just the opposite side of the Earth, to understand what it's passing through? I just think that is so cool. A little bit of math involved there, right? So we have the crust on the outside, going from the crust towards the core. We have the mantle, and then in the center we have the core. So let's look a little bit more at kind of sub-layers within that. Okay, so we have the asthenosphere, which is kind of fun to pronounce. The asthenosphere, I hope you can see this. This gray is this gray right here, and if you go down just a little ways, you're going to run into this asthenosphere. The asthenosphere is the kind of slippery liquid sort of, that's my letter L, liquid sort of region that our plates are going to float around on. Let's see. Then we have the lithosphere. Now the lithosphere, think of it, is actually the crust and the top part of the mantle. So the lithosphere, and we're going to see a slide here, and we're going to talk about plate tectonics, the fact that the Earth's crust is broken up into chunks that floats around. It floats around on the asthenosphere, but the lithosphere is the crust that floats. Okay, so the lithosphere is the crust and the top part of the mantle. And it's when we talk about plate tectonics, the lithosphere are the plates that are floating around.